Okay, good evening and a very warm welcome to all of you for this very special occasion. So we are having this Subhashish Nag Memorial Endowment Lecture. I will say a few words about this endowment lecture first. Subhashish Nag Memorial Endowment Lectures was instituted in the year 2002 through the generous contribution of Mrs. Shutapa Nag, wife of Subhashish. It aims to promote research in mathematical sciences by inviting to math science an eminent mathematical scientist, one each year, to deliver a series of lectures, the first of which is designated as the Subhashish Nag Memorial Endowment Lecture. A few words about Subhashish. Professor Nag was born 14th August 1955. He obtained his PhD from Cornell University, Ithaca, New York. He joined math science in 1991. He worked in the area of complex analytic geometry, particularly Teichmüller theory and its relation to string theory. He won the prestigious Bhatnagar Award and passed away the same year, 1998, at the young age of 44. He set for himself and others high standards of mathematical achievements. He was an inspiring teacher and pursued mathematical research with great passion. Some people in the audience already have known Subhashish Nag personally, but there are a few, particularly my younger colleagues haven't met him, so we have a photo of him. Now I request Indranil Biswas at Tata Institute to introduce the speaker.
Well, our this evening speaker is Professor Jacques Hurtubise. He is affiliated to McGill University at Montreal. He works on the interface between analytic and algebraic geometry. He did his PhD from Oxford. I think his supervisor was none other than Hitchin. Well, I invite him to...
I was wondering about a subject, and this is what I do, of course, but it was also a little bit embarrassing because I'm coming to a certain degree to the one of the fountainheads of the subject in Chennai with Narasimhan, Seshadri, Ramanan, and many others who've done far more illustrious things than I've done in this subject. So I thought I'd try to give it a little bit of a twist. It turns out that it's a good twist because part of the audience is in physics, and there's a bit of a physical theme that comes through it. And I actually discovered just now that there's another twist, which is that one of the examples I'm going to talk about is actually linked to the work of Subhashish Nag. So it's a special pleasure to give this talk. It's a fairly elementary talk, or at least I hope it is. Not too many new results in a way, but there are a certain number of puzzles that come out of this subject, and I suppose one of the aims of this talk is to share my confusion. So if you come out of the talk as confused as I am, then I've won. That being said, okay, but what is a moduli space? Well, you have a set of geometric objects, and so you'd like to sort of arrange these objects in a nice space. So, in other words, understand what it means to vary them continuously, describe this set with a natural topology, compute its topological invariance, and basically see how it's made. So sometimes a moduli space is very simple. If you're looking, say, at the set of complex lines through the origin in complex n space, well, that has a moduli space, and the moduli space is the projective n space, n minus 1. So this is a sort of, well, a very simple example of the family of all lines. You can replace lines by planes, and the family of planes is called the Grassmannian. Basically, because any plane has or a generic plane can be described as a map from Ck to Cn minus k. So the most planes will be graphs of maps. It's only when the plane hits the vertical that this description fails. But in general, you're seeing that you're getting most of the Grassmannian described simply by a k by n minus k matrix. I should say that these Grassmannians seem to come up as universal spaces all the time. If you're a topologist, you know that it's the basic building block for what's known as a classifying space for vector bundles. In some odd way, they seem to be universal examples here too, in that if you sort of actually trace through the construction of a moduli space in algebraic geometry right back to the origin, you end up in one of these. So in some sense, once you've understood the Grassmannian, you have everything. That's not true. Okay, so you want to classify these objects. You're assuming that they come in some continuous, smooth, or algebraic families. And of course, one way, how do you get a family? Well, you generally try to think of them as living over some base manifold. So you've got a base, manifold, and here my objects will be lines. And if you fit them all together, you're getting a plane. So that the inverse image of each point is one of the objects in your family. So a moduli space will be a space M that for any family, there's a map into this moduli space that it corresponds to. Now, ideally over this space, you'd have a universal family, and then you just get the thing by basically pulling it back. That doesn't always happen, so we'll just stick with this family here. What it does mean is that each point in that manifold somehow describes a different object. Now, I gave you two very simple examples when we started, but then, bad things can happen in more complicated examples. And I'm just going to illustrate, or try to illustrate with a very simple example, two things that can go wrong. So one of the examples is simply a projective curve. Fix the degree, and it's basically in the plane. So it's basically given by an equation. And that equation determines the curve. Now, if you rescale the coefficients, of course, it doesn't change anything. But basically, the moduli are those coefficients a, I, j, k. And if I've counted right, that should give you a projective space. The trouble is that family, you've thrown in some extra stuff. The type of thing you've thrown in is precisely this sort of bad curve here. Well, you see, it's not really a curve. It's like a curve that's been thickened. X equals 0 would be a curve, would be a line. But if you just take a certain amount of repetition, you're getting these curves. So there's a bit of a trade-off. You can get a nice space, which would be this. It's compact. It's closed. Everything is good. But then you have to throw in some bad stuff, or you can throw out the bad stuff and get basically an open set in this. So that's an example of something where there's a trade-off, but basically both solutions would be fine. This one's a little bit more complicated. So I'd like to consider conjugacy classes, and basically I'm just staying inside the complex numbers. So you know that each matrix has a Jordan form. So you think, okay, I want to classify conjugacy classes. They're given by Jordan forms. Okay, so it's done. But not quite. And this is the example that sort of causes difficulty. As long as the eigenvalues are all distinct, that's a perfectly good classification, though there is an issue of ordering them, right? Because it's, you know, it's up to order. But if you consider that family, where epsilon is the parameter, as long as that epsilon is non-zero, all of these matrices are conjugates. So it's the same point in your putative moduli space. On the other hand, when epsilon is equal to 0, you all of a sudden flip into a different conjugacy class. So you have two objects, basically, and they're represented by a continuous family. So this doesn't give you a nice space. And here the canonical trick is to throw things out. So here, for example, what you do is just allow classes with a cyclic vector, so maximal Jordan blocks. And then, for example, you could give a rational canonical form as your modulus. So the moral is sometimes they're bad objects that you just exclude, and the good ones tend to be called stable or semi-stable objects, and they're the ones you keep in your moduli space, and the bad ones you throw out, or in modern jargon you say it's a stack, and then all sins are forgiven. So you have to either add in extra things or throw things out. So that's a little sort of caveat. Wait a minute. Now, the sort of twist I wanted to give on these lectures was to link the spaces to some infinite dimensional spaces. They're spaces that in some sense have physical content. They're spaces that are in some sense simpler. You go to infinite dimensions, but there's some well-established tools of topology, for example, to understand these infinite dimensional spaces. And you try to understand basically how the space of objects you're interested in, M, is linked to this bigger, there we go, space. So often this space M is a space of minimal energy configuration. So you've got an energy functional, you minimize it, variational problem, very physical. If you want, it's the classical versus the quantum space. The classical space, or the space of least action solutions, and the quantum space is the space of all fields. And you try to compare the two. The other example would be the string theoretical one, where an infinite dimensional integral reduces to a finite dimensional one. So, for example, if you're integrating over all conformal classes for surfaces, so for string theory, and your integral is conformally invariant, you end up with an integral on the moduli space of Riemann surfaces. So that's the classical example, and that, of course, is what links to the work of Professor Nag. So I'm going to be looking at three cases. The first case is a case of holomorphic vector bundles on both a surface, a complex curve, therefore a Riemann surface, so there's always this ambiguity. It's a two-dimensional real surface, but of course it's a complex one-dimensional curve, and a two-dimensional complex curve. So, in other words, a four-manifold. So I'm going to be looking at those cases. That's case one. Case two is a similar, in many ways similar signal. It's the sigma model. It'll be maps from a surface to a manifold. So case two, maps from a surface to a manifold. And the third case is, in some sense, the sort of joker in the pack, and it's looking at integrals on the moduli spaces of Riemann surfaces. So I'm going to be looking through at these cases and trying to sort of highlight some of the nice things that happen and some of the things that don't. Okay. So this is the first case, holomorphic vector bundles on a complex curve or a complex surface. So you want a holomorphic vector bundle over X, and you want the moduli space of all holomorphic vector bundles. So what is a holomorphic vector bundle? Well, it's a space over X whose fibers are complex vector spaces. And you want the vector space operations to be holomorphic. So you have a space E over x. You can take a map backwards, so going up and coming down takes you back to the same point. And, but once you're up here, you can, of course, add, multiply by functions, and you want those operations to be holomorphic. Now, what is it to be holomorphic? Well, it's solving the Cauchy-Riemann equations. So the sort of freedom you have here is to specify which Cauchy-Riemann equations you're going to solve. And as you vary the coefficients of the equation, you'll be varying your holomorphic vector bundle. So how do you specify Cauchy-Riemann? You give one of these d-bar operators. And the kernel of this d-bar operator is holomorphic section, no matter which open set you're looking at. So what do they look like? Well, they basically look like the standard d-bar operator, because you're on a complex surface, so you know what it means to take complex derivatives. But as these are vectors, so that you're acting on a vector, then you sort of multiply this by a matrix. And invariantly, or at least in a local basis, it'll be a matrix of forms. And in two complex dimensions, there's an integrability condition. So you have to have that constraint. Otherwise, you can't, well, you can solve it in one direction or the other, but you want the two directions to be compatible. Okay, so this is the objects you want to understand. Good. Now, what happens here is that your there's an infinite dimensional group of symmetries that acts on this. So you have your d-bar operators. I'm just giving the coefficients. And if you change bases, basically, this is how that matrix changes. So in other words, you've got one basis that's varying from point to point. You apply change of basis, g of x. And this is how that operator looks like in the new basis. So you have two pictures. One, basically, if you're on I should have said both surface, all my x is a compact manifold. So everything's compact here. And so, just for general reasons, you know that you've got this finite dimensional space. It's going to be a moduli space. There are sort of ways of building it using algebraic geometry. But there's also an infinite dimensional picture. So you've got a family of operators, but you're quotienting out by an infinite dimensional group of what's called gauge transformations. Okay, so two pictures. Good. Okay. And now you do a little trick. I'm going to complete the d-bar operator to not only, so that's taking a derivative in the, if you want, the anti-holomorphic directions. I'm going to also take it in the holomorphic directions. And I'm going to do it basically by pretending that the basis I'm in is unitary. So I complete this to a full covariant derivative, nabla if you want, by just imposing, whoops, it is. Oh, there we go. Imposing this constraint here. Now what I've got is sorry about that. I've got inside these sort of complex valued matrices, I've got the unitary valued matrices. So I've got unitary gauge transformations. And so on the space of all connections, I quotient out by the unitary ones. I've still got this thing. So there's a vestigial piece of this that's still acting. And so, so the GC orbits are still there on this space. Okay, so now I've got this space here. And I'm now going to introduce a new thing, which is just a curvature, so that in terms of this, these two matrices, there's a formula that expresses it. And I take my energy just to be the L2 norm of the curvature, so I integrate the curvature. Right? And now the picture I want you to sort of think of is I've got an energy So I've used E into, and I've got sort of the orbits in my space of gauge transformations. I've got an orbit, and the game is going to be that moving around in this orbit to try to get down to minimal energy. And those are going to be my sort of special objects. So I've already quotiented out by the unitaries, but I've still got this thing left, and the idea is to sort of push yourself down to here. Okay. And there are two beautiful theorems. One is, of course, the Narasimhan-Seshadri theorem. So for a curve, and just to make life easy, I'm going to fix the degree to be 0. And you want to be able to move the energy to 0. And then what happens is and you can, as long as this bundle, like I said, wasn't one of those bundles that you had to throw out. If it wasn't stable, so this would be the sort of 0 energy, and I'll just put C here. And if it's not stable, what happens is you sort of end up, when you minimize the energy, you end up at a higher critical point. And so this is stable, and that is not. Okay? And so in other words, you've described, through this, you described your moduli space as of stable objects as the minima of the energy. Now for Donaldson, using sort of generalizing this theorem, and actually sort of using sort of more, well, sort of direct, if you want, variational techniques, did the same thing for a surface, and again I'm just going to take the degree to be 0. And now you can't actually force the energy to 0. There's an irreducible bound that you get, and this bound is essentially caused by the fact that for a surface, there's one topological invariant, which is the degree. You've killed that. But there's a second one that often gets called the charge, or second Chern class. And you need some curvature to represent that second Chern class. So you can't really force it to 0, but you can push it down to be the minimum possible, and you get this algebraic constraint on the curvature of it being what's called anti-self-dual. So again, you can stay in the complex orbit to the anti-self-dual ones, if and only if it's stable. Sorry? Oh, polystable, sorry, yes. So the story is basically that your holomorphic moduli will be the same thing as the anti-self-dual moduli. So you get this description again, this moduli space is sitting inside this space of all connections. They have to satisfy this integrability condition, but they're sitting there. Okay. And now, okay, we've got these complex orbits. Well, just forget about that group and just think of the energy and try to think of the relation that energy gives you on the topology. And there's a well-known theory for this, Morse theory, that tells you basically how the topology of the critical sets sort of builds up the topology of the whole. And the basic idea is that as you start at the bottom, Okay, you've got a sort of standard piece. It's basically just this piece thickened here. As you move up, as long as you haven't hit another critical point, nothing happens. It stays the same. And it's only when you hit the critical point that there's a sort of phase transition, or something changes, and you've changed your space. But it basically allows you to describe the topology of the whole in terms of the topology of the pieces. And Etienne Bott, in a paper written now more than 30 years ago, actually sort of turned this on its head, because what they knew about was the topology of the big space. They could, by induction, basically sort of inductively suppose they knew the topology of the higher critical points, and so they get the topology of this space by essentially, if you're looking at the common topological invariants, which are, say, homology groups, you sort of take the homology of this, you subtract this, and you get that. So that's the case for curves, and then you can get the homology or cohomology. You can get more, actually. You can get the ring structure, and there's a process called localization. This thing is actually a symplectic manifold, and there are sort of ways of computing integrals on this that essentially give you the ring structure. But again, it's getting the topology of the minima, the moduli space, from the whole minus the other critical points. If you're looking at a surface, then there's a phenomenon that happens that, at least from the analysis point of view, is explained by this property of bubbling. What happens basically is you're trying to minimize energy, and instead of doing what a good variational problem would do, which sort of spread it out and smooth it and make it, as close to a constant as possible, for a surface, the energy can concentrate, and will concentrate at a point. And in fact, it always concentrates on dimension 0 sets, so in basically a union of points. And it concentrates essentially to a delta function. And then in the limit, you just erase that delta function, and what's left is essentially a configuration of a lower charge. There was a conjecture, which I gave a proof of with my colleagues a while back, which says that this bubbling sort of is a failure. This failure of compactness would mean, in theory, that the big space and the small space aren't linked terribly well. But stably they are. So as you increase this charge, make it big, then you're capturing more and more of the topology of the big space with the topology of the small space. So as you vary charge, this space doesn't change, basically. It's always the same. And this one is getting bigger and bigger. It's growing by essentially its dimension is a multiple of k, or at least a linear function of k. And as you're taking that up to infinity, so you've got a bigger and bigger manifold, and it's copying, or it's imitating the topology of this bigger space through a range that is getting bigger and bigger. Okay, so you're increasing the charge, and you're capturing more and more of the knowledge of this space. This is for, in physics, what would be a four-dimensional gauge theory. And so there's another example, which I think is a oh dear, it's not supposed to be a Kabler metric actually, but so Kähler, sorry. So you're taking a compact surface, you're giving it a metric, compact Riemann surface, and you're taking a complex manifold, again with a Kähler metric. And now the energy is going to be the harmonic map functional. Oops. But anyway, within the smooth maps, again, a big infinite dimensional space, you'll have the holomorphic maps. Now, just noting that there's some x's for which this is empty, so it's kind of a dull problem. So you tend to stick to varieties for which there are lots of maps, and so rational varieties. And one example, when you're taking sigma to be the Riemann sphere, is what's called a rationally connected variety, so that any pair of points can be joined by a rational curve. Okay. So you have, as I was saying, this energy functional. And the critical points of this energy functional are called harmonic maps. Now, holomorphic maps for between two Kähler, for Kähler surface into a Kähler, a holomorphic map in our case will be harmonic. So it minimizes, it's a critical point of the energy, but what's more, if you have a holomorphic map in that homotopy class, so with up to deformation, then it actually minimizes the energy. And here, if you try to minimize energy directly, so you just squeeze it down, again you get this bubbling phenomenon, and here it actually is a bubble. So so here's my target, x. And I'll just draw a one-dimensional curve. And you've got an image of your curve. And as you're trying to lower the energy, what's happening is that a smaller and smaller area of your curve is actually, in some sense, growing bigger and bigger, like that. And in the limit, you've just got a little point, and in the target, you've got a little sphere that's attached to it. And so you actually have formed a bubble. Now, the general theorem, which is Wolfson and Parker, I believe, is that what you get, in fact, is a bubble tree. So you'll have... now I'll try to draw a real surface. Well, anyway, here we go. So I'll have a surface, and you'll have little spheres, and then you can have spheres on spheres, and so on. Okay? So the things that get added to the core are always spheres. And they call it a bubble tree, which is quite cute. And here also you get topological stability, and this was examined by a whole bunch of people. Graham Siegel proved the first example when X was a projective space. Francis Kerwin did Grassmannians. My collaborators and I did flag manifolds, Martin Guest, toric manifold. And you can go all the way up, and the farthest we got was an equivariant compactification of a solvable group. And it's the same thing as for this Atiyah-Jones conjecture. You get the big space being approximated by the small space, and as you increase the charge, of course, you're getting more and more well, as you increase the charge, the space is getting bigger, basically, and it's sort of eating up the space of C infinity curves. There are theorems, for example, for special cases. If you're taking, say, maps from P1 and you take x equals P1 also, there's a theorem that says there are no higher order critical points. So you're seeing exactly the failure of Morse theory in the gap between this and this. And so the gap is all due to that bubbling. Other comments, you'd like to, these have some big groups acting basically, and that's what saves your, allows you to function, but more generally you'd kind of hope that this was true for X, a rationally connected variety. In other words, as long as you've got lots of holomorphic maps, you can mimic the continuous maps. Another comment perhaps, if you had, you could actually redo the case of the anti-self-dual gauge fields, in other words, the previous case, by taking X to be an infinite dimensional flag manifold. So if you go to infinite dimensions, this actually subsumes the previous case. So you get some nice topology there. Sorry? Oh, good point. Here your K is in the cases that you look at is an integer vector of integers. So you can imagine for the varieties we're looking at least, they're sort of divisors at infinity, and you're intersecting each of these with a certain multiplicity. And each one of them is giving you a degree. So there's a multi-degree, and so again, because it's holomorphic, these things have to be positive numbers, and you want them all to go in infinity together. So essentially, K is this norm here is the minimum of the entries, and this L as a function of that norm is actually again a linear function. So in other words, linear minus a constant, basically. The same thing works with the, and in fact, it enables you. So there are various proofs of this Atiyah-Jones conjecture for, UN, so vector bundles, orthogonal bundles, symplectic bundles. If you use this formalism, you can do it for any gauge group, basically. So you just cover the whole thing and do it at once. It also, changing the flag manifold, you can consider what's called Calerons. So there are other configurations of there are a whole bunch of. So it's a slightly more general theorem. So anyway, but you get this stability, and again, you're seeing that somehow, though the Morse theory is failing, asymptotically it's working, and it's still a bit of a mystery why it should be that way. Okay. The last example is one where we're going to do some integrals. And here it's, well, there are several proofs now, and I think it's fair to say that none of them really, I don't think the good proof has been found yet for what's happened. But it's really a surprising result. So you look at the space of all Riemann surfaces. So you fix, what do you fix? You fix a genus, so the number of holes in your surface. And these are holes of a different type. They're punctures. They're points. So you've got a Riemann surface, certain genus, and then n marked points. The points are ordered. And this thing has a compactification, again, rather in the spirit of that bubble tree, and that if you go to the limit, the things sort of pinch off into nodes. It's a little bit more complicated than that, but it's the sort of same idea. The stability, as I was saying, is there are only finitely many automorphisms. So basically, if you get a rational piece, there has to be marked points to sort of kill the automorphisms, and the same if you get an elliptic piece. Anyway, complex dimension, 3g minus 3 plus n. Okay, so again, it's a space that grows with g and n. Now you have line bundles on this space, and it's simply taking, you've got a surface, you've got a point. So for each of these surfaces and points, you get its cotangent space. So that's a complex line. And you do this for each of these, and you'll get a line bundle. Now, again, the topological invariance for these line bundles, basically a two-form, closed, psi I. And what you'll do is multiply these up and integrate them. So you take, define some numbers, and they're indexed by these things D here, and you integrate this on the MGN. And if there's no MGN that works, you just say it's 0. So if the sum of the DIs, right, this is a complex dimension, so it's 6G minus 6 plus 2N real. Each of these is a two-form. You add them up, and you get a form of the right dimension, you integrate. Now, you notice there's some symmetries here, but because basically you just labeled the points. So if you interchange the labels, it gives you the same thing. And what you do is you put all, whoops-a-daisy. Oh, there we go. So you put all of these together in a generating function. And you then add it all up, like that. And then you actually go to some people doing nonlinear equations, and you get what's known as the KdV hierarchy. So these are equations, Korteweg-de Vries equations, that govern the movement of nonlinear waves in a shallow basin. So what has that got to do with anything? And that's part of the mystery. They come, actually, people noticed that there were actually a sort of whole hierarchy of operators that commuted. And you take your generating function, you take its second derivative with respect to t0, call this u, and it solves this KdV hierarchy, and it actually solves it with a given initial condition. You notice you're getting flows, basically, for each I different from 0. So for 1, 2, 3, you fixed all your values to be 0 here. So flowing out from there, you're getting basically the arbitrary solution from this seed. Okay. So the question basically is why? Now there are proofs, and there's a beautiful proof due to Kontsevich and many other proofs since, and you think, okay, maybe this is a fluke. But there are other things that happen. You get, if instead of integrals on MGN, so these are, if you want, I've got a Riemann surface, so I can think of it as just a map of a Riemann surface to a point. Right? The point's not doing much, but I throw it in. Well, you can extend this to maps of the Riemann surface to a given space. And you can put conditions and things like this. But anyway, you define your integrals, you put them in a series, and you get similar functions. And lo and behold, for example, Okunkov and Parapande show that when you take the target to be the Riemann sphere, you get what's known as the two-toda hierarchy. So again, it's a classical integrable system coming from people who do this for a living. It's been there around for quite a while. And it solves this. That should be integrable hierarchy. But again, you use Hurwitz numbers. This time you count covers of Riemann surfaces over P1. So you count coverings of different type. Again, you get numbers. You make a generating series out of them. And you get this integrable hierarchy. Even more sort of astounding, Bertrand Hénard and Nicolas Arentin have this technique, which they developed using, they were working on random matrix models. And they basically take one curve, And it's not even a compact curve. All it is essentially a germ of a curve, or several germs, in C2, has branch points. From the branch points, they can calculate forms, and a whole hierarchy of forms, and then they calculate constants from these forms. Again, you put it into a series, add it all up, and it solves one of these integrable hierarchies. So, and then they link, of course, they get the Kontsevich model, they get the Pandalipande, these Okunkov-Palapande, Hurwitz numbers, all these generalizations, and they say, oh, this is, take this curve and take that curve. And the whole thing has a very oracular quality in the sense that, you know, they know which curve, and they're getting the right answers. But it's all, from a mathematical point, it's entirely astounding. Now, I said this was a lot about the interaction between spaces MGN and an infinite dimensional spaces. And here, in some sense, there's a surfeit of them. So maybe I'll try to describe a bit of the various sort of infinite dimensional players that are coming in. So the first infinite dimensional player is an infinite dimensional Grassmannian. So you take a vector space, or a Hilbert space, which is the L2 functions on the circle. You split it into two bits. These are Fourier series. You take the positive frequency Fourier series, you take the negative Fourier series. And now you build this is an infinite dimensional space, you build a Grassmannian of planes that are of half infinite dimension. So what does that mean? Well, you consider planes, W, like that, so that the projection this way is Fredholm. So a finite dimensional kernel and co-kernel. So it's almost H+. And you project this way, and the image is small. Now, there are various versions. It can be a compact projection, or Hilbert-Schmidt, or trace glass, but it's small. And you build the Grassmannian of these things. So you build a Grassmannian, and you do more. You actually build the Grassmannian, and there's a tautological bundle on this thing. Well, there's a tautological bundle, so for any plane, you take the vectors lying in that plane. That's not quite what you want. You want its top exterior power, and again, top exterior power is in infinite dimensions. You have to do a little dance, but you can do it. And so you build a line bundle, which is the determinant line bundle. Let's call it dead. Okay. And you build a canonical section, essentially, that lifting up from here. So in other words, as long as this projection is an isomorphism, this section is non-zero, and when this plane here hits the vertical, then it has a zero. So you build a section. That. Okay, so that's your basic geometry. And now you build a group. And what you do basically is take an infinite series, so Ti z to the I. These are Fourier coefficients. Okay, so this is the group basically well, how should I say? It has coordinates T0, T1, Tn, and so on. So it's an infinite dimensional abelian group, and it basically is just acts on L2 of the circle by multiplication. Okay, so you have your basic space, a group gamma plus acting on this space. Well, it's going to act, if it's acting on L2 of the circle, it's going to act here. So you've got gamma plus acting here, and gamma plus acting there too. Okay, and then the trick basically is to have you choose an initial point, W, and you act down here, take the section, and compare this with taking the section, then acting. So let's see if I can get this right. It'll be, say, e to the t times z on sorry, SW, no, I want the other way around. It'll be S of e to the t times z acting on W divided by e to the t times z acting on S of W. There we go. Okay, so you build this function. So you flow, take section, take a section, then flow. And the theorem is that this is a sort of universal solution of these hierarchies. So the word universal, of course, as in all these things, is to be taken with a grain of salt. If there are analysts in the audience, their toes are curling and they're sort of biting their cheeks, but it's a sort of general way of getting, should we say, all the nice solutions for these integrable hierarchies. They're variants. I've cut corners and things like that, but that's the general idea. So the first item, if you want infinite dimensional space, is where this solution lives. The second infinite dimensional space involve random matrix models. So again, here what they're doing is they're computing the expectation values of a family of observables, again parameterized by these t's. And that's the thing that eventually gives you this integrable hierarchy. And the third and very clever thing is that to solve this problem, Kontsevich actually uses a really lovely piece of mathematics describing Riemann surfaces, developed by Strebel during the 1960s. And it's basically giving a canonical metric with singularities on a punctured Riemann surface. So if I draw it for the punctured, say the three-punctured sphere, which one would tend to draw this way, well, you don't draw it that way. You draw it basically as a infinite cylinder. Okay, like that. Okay? So conformally, because you're just interested in conformal classes, you've got an infinite cylinder. The metric will have a singularity at this point. And it's essentially what you extract from this. Now, you have to put in extra data. You put in a perimeter P1 here, P2, P3, and correspondingly you'll have lengths on, say, L2, L3, and L1, so that P2 is actually L3 plus L1. It's coming around the back here. P1 will be L2 plus L3, and so on. Okay. So this is done using quadratic differentials. Okay, so an arbitrary Riemann surface, what does it give you? It gives you a connected graph. So I've got a graph that's living in the surface, and that's important. So you'll get a, say a graph, I'll draw it like this. Because the graph is living in a surface, it's got a cyclic order at the vertices. The general picture basically will have one puncture in each region. So each region of the, if you want, of the plane it actually corresponds to a puncture. So, for example, there are no sort of annuli in this picture. And so this graph with some lengths on it is actually specifying your surface. And so what he does, Kontsevich, is say, fine, we just consider the integral on the set of Riemann surfaces. Well, we just reduce it to an integral on the set of graphs, where your variables are these lengths. Well, that's good. Then you notice that basically the only graphs you need consider are trivalent, because the tetravalent ones and so on, or things where if you've got higher order valency at vertices, then this is a measure 0. Okay, so in other words, you get the integral on MGN to be a sum of integral on trivalent graphs. And the sum of these will be a sum on all trivalent graphs. So summing over all MGN is now an integral, a sum of all trivalent graphs. Okay, well, what does a trivalent graph have in common? Well, it's again difficult to imagine what's containing all these spaces. There is something that contains, in some sense, all these spaces. Is this an infinite trivalent tree? So just have a sort of branching out in all directions. So if I put lengths on that, so you're basically integrating over all finite quotients of this thing. And so one of the questions is there some sort of localization? And then, of course, the question is, fine, how do you get back to this Grassmannian? But there's obviously some infinite dimensional geometry there. The thing, in a sense, is coming from physics. It's the original conjecture by Witten was saying, well, I've got this model for gravity and I've got this model for gravity. They should give the same answer. He doesn't say how. So, again, there's some infinite dimensional spaces there. The only thing is we're not actually sure what they are. So, thank you.
Let's thank the speaker again.
No.